Hi, I'm Nathan Sahelijo. I'm a graduate student at Boston University, and today I'll be talking to you about a graphical user interface for the interactive analysis of mutational signatures. Cancer development is driven by the accumulation of somatic mutations. These mutations derive from endogenous mutational processes like defective DNA mismatch repair or DNA structural damage, which can be accelerated by exogenous processes through the exposure of mutagens like ultraviolet light or tobacco. Each unique process leaves behind a distinct mutational signature that can be modeled by counting the single base and double base substitutions, as well as insertions and deletions. Understanding that the mutational catalog of a genome comes from the aggregation of multiple mutational processes, we can deconvolute the mutational catalog into its component mutational signatures and corresponding levels of exposure. We developed an R-Shiny graphical user interface to allow non-computational users to perform deconvolution analysis using the music-to-TK pipeline. Somatic mutations can be imported from mutation annotation format or variant call format files using the import tabs. TCGA datasets can also be downloaded and imported directly into the application. Users can also import sample annotations for downstream analysis like differential exposure analysis. After building the mutational counts matrix, the deconvolution can be performed to discover signatures or predict exposures using a latent Dirichlet algorithm or negative matrix factorization. The Discover tab deconvolutes a predefined number of signatures from the mutational counts matrix, as well as the exposure levels of each signature. The Predict tab estimates the exposure levels of a predefined set of signatures across all samples. Music-to-TK includes the latest cosmic signatures for prediction, but users can also upload signatures as music result objects. In Figure 5a, we visualize a set of 8 signatures discovered using the LDA algorithm applied to a mixture of 567 lung adenocarcinoma, 492 lung squamous cell carcinoma, and 467 skin cutaneous melanoma samples downloaded from TCGA. In this bar plot, the X and Y axes correspond to the mutation type and probability of occurrence. These signature probability distributions represent the distinct mutational footprints left by each mutational process. In this case, the mutation types include single base substitutions with up and downstream context bases. This means the bar plot spans a total of 96 possible mutation combinations. In 5b, we use the exposure subtab to create a stacked bar plot representing the proportional signature exposures for the top 400 samples, ordered by the exposures of signature 1. The exposures indicate the amount of each signature present in a sample. Besides the proportional bar plot, exposures can also be visualized using box plots, which can be grouped via annotation, as in Figure 5c. Users can also visually analyze differences in signature exposures across samples using UMAP. In Figure 5d, we show a scatter plot of each sample according to the exposures of all 8 signatures reduced to 2 dimensions using UMAP. Skin cancer samples are cleanly separated from the lung cancer samples according to their signature exposures, indicating a possible difference in etiology. The Compare tab allows users to compare any 2 collections of signatures using cosine similarity or Jensen-Shannon divergence. Any signature pair whose similarity is greater than the user-provided cutoff will be displayed in a downloadable table. This is practical when users want to compare the discovered signatures to previously identified signatures in other studies. Cosmic signatures are again included by default, but users can upload any set of signatures for comparison. From 6a, we see a strong association between signature 1 and Cosmic's tobacco smoking signature. To quantitatively compare exposures, we implemented several differential analysis methods, including the Wilcoxon rank sum test, the Kruskal-Wallis test, and negative binomial regression. To run differential exposure analysis, users will need to have uploaded sample annotation data. For the Wilcoxon rank sum test, users can specify the sample groups to compare. The exposure differential analysis tab is useful for identifying signatures unique to certain sample subtypes. In Figure 7, we see significant differences in signature exposures between lung adenocarcinoma and skin cutaneous melanoma, except for signature 7, which is suspected to be the spontaneous deamination signature. Finally, the Shiny interface also includes a clustering tab that lets users perform clustering analysis on exposures and visualize the results. Users can choose from a variety of clustering algorithms, including k-means, hierarchical, and Clara. The results of the clustering analysis are displayed using UMAP. Depending on the option selected, users can visually compare the proportional exposures grouped by cluster. Or if sample annotations were uploaded, users can also create a scatter plot grouped by cluster and annotation. Figures 8A and B highlight the differences in signature exposures between cluster groups. Cluster 1 contains mostly lung samples, while cluster 2 is almost entirely skin cancer. From figure 8C, signatures 1 and 5 are highly enriched in cluster 1, which are the lung samples, while 3 and 8 are enriched in cluster 2, the skin. Of course, the Shiny interface also includes plotting by heat map. By including annotations, these heat maps can be generated from subsets and can be annotated according to the specified sample annotation. Similarly to 8C, figures 8D shows signature 1 and 5 are enriched in lung samples, while 3 and 8 are enriched in skin. All results are downloadable as RDS objects, which can be re-uploaded at any time for additional analysis. To summarize, we developed an R-Shiny graphical user interface for the Musica.tk package to provide a framework for discovery and analysis of mutational signatures for non-computational users. The user-friendly interface streamlines the Musica.tk pipeline by providing a step-by-step workflow that includes pre-processing, deconvolution, and downstream exploratory analysis. Thank you for listening.